Let's talk about a strange and powerful idea. It's called spontaneous symmetry breaking. The name sounds complicated, but the core idea is simple. It's about how things get their shape, how the universe gets its texture. It explains why the world looks the way it does. And it all starts with a perfect balance that gets tipped over. Imagine a pencil, a perfectly sharpened pencil, and you balance it on its tip. This is a very symmetric situation. You can walk around the pencil in a circle. From every angle, it looks the same. The force of gravity is pulling it straight down. All the forces are perfectly balanced. The laws of physics governing this pencil have a perfect rotational symmetry. Nothing prefers left over right or forward over back. But we know what happens next. The pencil can't stay there. It's a unstable position. The tiniest vibration, a whisper of air, will make it fall. And when it falls, it has to choose a direction. Well, it will fall one way, not every way at once. It might fall towards the window or towards the door. But it will pick one specific direction. Now look at the pencil lying on the table. Is the situation still symmetric? No, the symmetry is gone. The pencil is now pointing in a particular direction. The rotational symmetry has been broken. If you walk around it, it looks different from different angles. Here is the key point. Did the laws of physics change? No. Gravity still works the same way. The rules are still perfectly symmetric. The rules didn't have a preferred direction, but the outcome did. The final state of the pencil, its lowest energy state on the table, does not have the same symmetry as the underlying laws. The symmetry was broken spontaneously. Nothing pushed the pencil in a specific direction with a specific plan. It just fell. The choice was random. Any direction was equally likely at the start. But a choice had to be made. This is the heart of spontaneous symmetry breaking. The rules of the game are symmetric, but the result of the game is not. The system itself chooses to break the symmetry to find a stable state. This isn't just about pencils, it happens all around us. Think about a dinner party. You have a round table. The host places a fork and a spoon at every setting. But then, at one spot, they place the bread plate exactly between two settings. Now everyone has a choice. Do you take the bread plate on your left, or the one on your right? The situation is initially symmetric. Everyone has the same dilemma, but the first person to reach for a plate breaks the symmetry. If they take the plate on their left, then the person to their left must also take the plate on their left. The choice propagates around the whole table. Suddenly, a rule has been established. Everyone takes the left plate. The final arrangement is ordered, but it's asymmetric. The opposite choice, everyone taking the right plate, was just as possible, but one state had to be chosen. The system settled into one of two possible ground states, neither of which had the original left-right symmetry of the initial dilemma. Physics is full of these situations. The universe is a system that is constantly trying to find its lowest energy state, its most comfortable position, like the pencil on the table, not balanced on its tip. We call this lowest energy state the ground state. Sometimes the most stable, lowest energy ground state is one that has less symmetry than the laws that govern the system. Let's take a more physical example. A magnet. Think of a block of iron. Above a certain hot temperature, it's not magnetic. Inside the iron are tiny, microscopic magnetic domains. You can think of them as tiny arrows. When the iron is hot, these arrows are all pointing in random directions. They jiggle around chaotically. If you average them all out, there's no overall magnetic field. The block is symmetric. No direction is special. It has no north pole or south pole. Now, let's cool the iron down. As it gets cooler, the little arrows start to feel each other. They want to align. It's energetically favorable for them to all point in the same direction. At a specific temperature called the Curie temperature, something amazing happens. They all snap into alignment. But which direction will they choose? The laws of physics don't care. Up, down, left, right, any direction is as good as any other. The choice is random. Spontaneous, but they will choose one. Suddenly, all the arrows are pointing more or less in the same direction. Now the block of iron is a magnet. It has a north pole and a south pole. It is no longer symmetric. It has a preferred direction in space. The rotational symmetry is broken, but again, the laws of physics governing magnetism didn't change. They are still perfectly symmetric. The ground state of the magnet, however, is not. The system spontaneously chose a state of lower symmetry to achieve a state of lower energy. This transition from a symmetric state to a less symmetric state is a phase transition. Like water turning into ice. Liquid water is very symmetric. The molecules are all jumbled up, moving randomly. On average, it looks the same in all directions, but when you cool it, it freezes into a crystal. ice. A crystal has a very specific ordered lattice structure. The atoms are locked into a grid. This grid is not symmetric in the same way the liquid was. It has broken the original rotational and translational symmetry of the liquid. The atoms had to choose a specific orientation for their crystal lattice. It's another example of spontaneous symmetry breaking. To really understand how physicists think about this, they use a famous mental picture. It's called the Mexican hat potential. Imagine a sombrero. It has a high point in the very center, and then it slopes down into a circular trough, or brim. Now, imagine a small ball. We place this ball right on the tippy top of the hat center. This position is perfectly symmetric. It's balanced, but it's not stable. It's a state of high energy. The slightest nudge will cause the ball to roll down. Where will it roll? It will roll down into the circular brim at the bottom. The brim is the set of all the lowest energy states, the ground states. Once the ball is in the brim, it's stable. It has found its comfortable place. Notice two things. First, the hat itself, the set of all possible states, is perfectly symmetric. You can rotate it and it looks the same. The laws of the system are symmetric. Second, for the ball to be in its lowest energy state, it must be somewhere in the brim. It can't be at the top, but if it's in the brim, it's at one specific point. For example, the point closest to you. Or the point to the left. It has to choose a location. By choosing a location in the brim, the ball has broken the rotational symmetry. The system, with the ball at a specific spot in the trough, is no longer symmetric. The state itself is asymmetric, even though the rules, the shape of the hat, are perfectly symmetric. The system spontaneously rolled down and broke the symmetry. This Mexican hat picture is more than just a cute analogy. It's a mathematical graph of the energy of a physical field. The height of the hat represents the energy. The position of the ball represents the value of the field. In many theories in physics, the universe is filled with various fields. And these fields, like the ball, want to be in their lowest energy state. In the very early hot universe, there was so much energy that the fields were like the ball jiggling around on the very top of the hat. The system was symmetric. But as the universe cooled and expanded, the energy dropped. The fields rolled down into the trough of the hat. They settled on a value, a specific, non-symmetric value. This process, happening all over the universe, is what gave the world the structure we see today. This has a fascinating consequence. Look at the ball in the trough of the Mexican hat. It can be at any point along the circular brim. Let's say it's at the point closest to us. What happens if we give it a tiny push, but we push it along the brim? It will roll around the circle with almost no effort. It costs no energy to move from one ground state to another in the trough. They all have the same low energy. But what if we push the ball up the side of the hat, away from the brim? That takes energy. That's a harder push. In the world of quantum field theory, these different kinds of pushes or excitations correspond to particles. A push up the side of the hat, which costs a lot of energy, corresponds to a massive particle. A push along the trough, which costs no energy, corresponds to a massless particle. A physicist named Jeffrey Goldstone figured this out. Goldstone's theorem says that whenever a continuous symmetry is spontaneously broken, a massless particle must appear. This particle is called a Goldstone boson. It represents the system moving cost-free between its many different, equally good ground states. It's the physical manifestation of that flat trough in the Mexican hat potential. For a while, this was a problem. Physicists saw spontaneous symmetry breaking as a great idea, but it seemed to predict all these massless particles that we don't see. And for example, in the theory of the weak nuclear force, the force responsible for radioactive decay, a model with spontaneous symmetry breaking predicted Goldstone bosons. But we've never found them. So, the idea seemed like a dead end for particle physics. Then came the breakthrough, a brilliant idea from several physicists, including Peter Higgs, Francois Englert, and Robert Brout. They figured out what happens when you combine spontaneous symmetry breaking with a special kind of symmetry called a gauge symmetry. This is where things get a bit more complex, but the idea is beautiful. The theory that describes the electromagnetic force and the weak nuclear force, called the electroweak theory, has a very high degree of symmetry. This symmetry is essential for the theory to make sense. And this symmetry requires that the particles that carry these forces should be massless. For the electromagnetic force, this is fine. The force carrier is the photon, and the photon is indeed massless. But for the weak force, this was a disaster. Experiments showed that the particles that carry the weak force, the W and Z bosons, are extremely heavy. They're among the heaviest particles we know. So the theory said they should be massless, but reality said they are massive. The theory was broken. Spontaneous symmetry breaking came to the rescue. The idea was this: what if the entire universe is filled with a field? Let's call it the Higgs field. And what if this Higgs field behaves just like our Mexican hat? In the very hot early universe, the Higgs field was at the top of the hat. It had a value of 0. The electroweak symmetry was perfect. All the force carriers, the W, Z, and photon, were massless. Everything was symmetric and simple. But as the universe cooled, the Higgs field underwent a phase transition. It spontaneously broke the symmetry. The ball rolled down into the trough. The Higgs field acquired a non-zero value everywhere in space. The vacuum of space itself is now in this broken symmetry state. Now, here is the magic. The W and Z bosons interact with this background Higgs field. They feel it. Moving through this non-zero Higgs field is like trying to run through deep snow. It slows you down, it gives you inertia. This resistance to motion is what we perceive as mass. So, the W and Z bosons get their mass from their interaction with the symmetry-broken Higgs field. The photon, on the other hand, does not interact with the Higgs field in this way. It zips through the Higgs-filled vacuum as if it weren't there, so it remains massless. This elegant idea, called the Higgs mechanism, explains why the weak force is so short-ranged, because its carriers are heavy while the electromagnetic force is long-ranged because its carrier is massless. It unifies them at a fundamental level and then explains their differences at low energies through spontaneous symmetry breaking. But wait, what about the Goldstone bosons? The theorem said we should get massless particles when the symmetry is broken. Where did they go? In this special case of breaking a gauge symmetry, something wonderful happens. The would-be Goldstone bosons don't appear as independent particles. Instead, they are eaten by the W and Z bosons. They become a part of the massive W and Z bosons. A massless particle is simple. A massive particle is more complex. It has an extra component, an extra polarization. The Goldstone bosons effectively become this extra piece. So the puzzle was solved. The massless particles are avoided and the force carriers get their mass. It's an incredibly neat package. And there's one more piece. Remember the Mexican hat? We talked about two kinds of pushes. The easy one along the trough, and the hard one up the side of the hat. The easy pushes were eaten by the W and Z bosons. But what about the hard push? The one that costs energy. That excitation, a jiggle in the Higgs field itself, up and down the side of the hat potential, would appear as a new particle. A massive particle. This particle is the Higgs boson. For decades, this was just a theory. A beautiful, compelling theory that held the standard model of particle physics together, but a theory nonetheless. The final piece, the Higgs boson, had to be found to prove it was right. Physicists built the largest machine in human history, the Large Hadron Collider LHC, in large part to find it. They smashed protons together at incredible energies, trying to create enough energy to knock the Higgs field up the side of the hat and produce a Higgs boson. And in 2012, they found it. They discovered a new particle with the exact properties predicted for the Higgs boson. It was a monumental achievement. It was the confirmation that this strange idea of a universe-filling field that spontaneously broke a fundamental symmetry was actually true. The vacuum of space is not empty. It's filled with a Higgs field, sitting in the trough of its potential, giving mass to the fundamental particles that make up our world. Spontaneous symmetry breaking is not just a concept for particle physicists. It's a fundamental organizing principle of nature. It's the engine of complexity. Perfect symmetry is often simple, but also boring. A perfectly uniform gas is symmetric, but it has no structure. A perfectly balanced pencil is symmetric, but it's not a stable part of the world. The structures we see around us are the results of broken symmetries. The existence of crystals, magnets, and superconductors in condensed matter physics is due to spontaneous symmetry breaking. The formation of galaxies and large-scale structures in the universe might be seeded by tiny quantum fluctuations that broke the perfect symmetry of the early cosmos. Even on Earth, life itself is a festival of broken symmetry. The molecules of life, like amino acids and sugars, have a handedness. They come in left-handed and right-handed versions, mirror images of each other. The laws of chemistry are symmetric. They don't prefer one over the other. But all known life uses only left-handed amino acids and right-handed sugars. At some point in the origin of life, a spontaneous choice was made, and that choice has been passed down ever since. So, this idea, which starts with a simple falling pencil, scales all the way up to the fundamental nature of reality. It tells us that the world we live in is a broken reflection of a deeper, more perfect set of rules. The laws of nature may possess a pristine, elegant symmetry, but the world we experience, the ground state we live in, is the result of that symmetry being shattered. The universe had to make choices. It had to fall off the tip of the pencil. It had to choose a direction for magnetism. It had to choose a specific value for the Higgs field. And in these choices and these acts of breaking perfection, the complexity and richness of our universe were born. The asymmetry is not a flaw. It is the feature that allows for structure, for substance, for us to exist at all. The world is beautiful not because it is perfect, but because it is broken in just the right way.